Hello everyone and welcome to the first installment of Electrical Theory Thursday. Now if you didn't see my Tech Talk Tuesday that I posted on Tuesday, go back and watch that. I expect for the Tech Talk Tuesdays to probably be a weekly run. However, this Electrical Theory Thursday may just be every other Thursday, or maybe one Thursday out of the month, or something like that. It's probably not going to be a regular. Maybe the last Thursday of every month is what I'll do on that one, on this one. So anyway, today I'm not in the garage on the workbench. I'm still shuffling things around down there. So I've kind of put a lot of the amp work that I've been doing kind of on hold as far as videos go until I get that place set up exactly the way I want it set up. And also this weekend, my wife's sister and brother are coming up with their kids, and they're bringing my granddaughter with them, my 4-year-old granddaughter with them from Texas. So unfortunately my daughter can't come, but we get the mini daughter, the 4-year-old version of her. We'll get her up here for 4 or 5 days, so that'll be good. And during that time I'm probably not going to do any amp work at all, so definitely no videos coming. May not even get a Tech Talk Tuesday next week, but I'll try to squeeze a 5 or 6 minute video in there for that. But anyway, that's what I've got going on. Today on the Electrical Theory Thursday, what I want to go over a little bit is how to do the math and the algebra when doing design work. A lot of you guys out there are doing your own designs, and you're wondering, you know, how do you do this and how do you do that, and different things. And somebody had messaged me on SRT Amplification Facebook page. I guess they didn't want to put a comment in the YouTube, so they messaged me on Facebook, which, by the way, that is a good way to get in touch with me. If you don't want to put a comment on one of the YouTube videos, go ahead and you can drop me a message at my SRT Amplification Facebook site. So, but anyway, I've been getting into a lot of discussions with people on since one of the last videos I did with the series filament amplifier, exactly how to come up with the dropping resistors, how does that work, and then also it led into the discussion about putting filaments in parallel versus series, and even within the same tube, like a 12AX7, putting it in parallel or in series, and how all that works. Well, there's a little bit of math involved, and a lot of people think they know what they're doing because they've been told this is how you do it, but they really don't know the theory behind it. So that's what we're going to cover today, a little bit of the theory behind why things are designed the way they are. So if that sounds like something you'd be interested in, stick around and we'll put this on paper. So if you'll remember in one of the earlier videos, we had this circuit that we were looking at, and it had all the tube filaments in series with one another. And so we had our one of the 12 AT6s right here, and another 12 AT6 here, and then we had our 50 C5 here, and then we had our 35 W4 right here. And then we had this 75 ohm dropping resistor right here. So one of the questions that came up was if I wanted to design an amp with some of these older tubes, which, by the way, these types of tubes, you know, your 50s, your 35s, they had 25s, 70s. They had a whole bunch of different versions of these tubes back in the day. And the reason they had them is for an instance like this, we were going to use a series filament setup here and not use a power transformer. Especially on these low wattage amplifiers, you didn't need to raise the voltage for the plates very high in order to get what you're trying to get out of. You got to remember, back in the day, all your radios, record players, all that stuff was tube technology. So even your smallest little amplifiers that amplified your record player or whatever, was a tube amp inside, whether it was 1 watt or 1.5 watts or even half a watt, whatever it was. So this was a very good way of doing it. Nowadays, you don't see, 50s and 35s and stuff like that. Your common tubes are more in the 12 and 6 volt range. So, but anyway, that's just a little background. But so, if you're wanting to put together one of these things, because you run across these tubes all the time on eBay. Somebody may come across a lot of tubes that they bid on and get, and they got all these 50s and 35s, and they're just wondering what to do with them. Well, making one of these little single-ended, low-powered amps may be the way to go. Really, really cheap. You don't have to buy a power transformer or anything like that. And you could probably find a design online pretty easy. But if you just wanted to really know exactly why this is and how to do it, I'm going to show you the math on that. So what we have to do is, and what a lot of people do is they just add up their tubes. They say, okay, this is 50 volts, this is 12 volts. They just add up their tubes here. They say, this is 50 volts, this is 12 volts, this is 12 volts, this is 35 volts. But then that doesn't add up to 120. It's like 11 volts short. So then they're like, oh, 11 volts short. So, how do I get this? Well, I'm going to run through the math with you, exactly how this all works out, and we'll see. So what a lot of people don't realize, and what let me pull up the, this is a data sheet for several different types of tubes, but it's got the 50C5 in here. And what a lot of people don't realize is although it gives you the voltage for the filament, and it also gives you the for the heater filament, and also it gives you the current for that filament. What's behind the scenes there that really works this whole thing is there's a resistance value associated with this filament here. So what you have to do is you have to figure out what that resistance is. So at 50 volts, 150 milliamps, that comes out to somewhere around 330, if you do the math, it's like 333.33 repeating 3 ohms. So that is an actual resistance, okay? So if we find that for every tube that we have in the circuit, then we'll know exactly what we need for that dropping resistor at the end. Now, because these are in series, you have to use tubes that want to operate at 150 milliamps. You don't want to use a tube you don't want to stick a tube in there that wants 1.5 amps, like a EL34 or something like that. It's not going to work. Or any of these right here that that want to operate at 0.6 or at 600 milliamps or 450 milliamps or 300 milliamps. You want all tubes, because the filaments are in series. They're all going to have the same current on them. So if you have 6 amps running through your circuit, that's not going to probably be very good for a filament that was designed to only operate at 150 milliamps. Now these aren't exact numbers. Notice there's nothing on here that says max amps for your filament. All your max ratings are over here on the next page. Okay. And there's nothing in there that says, hey, you can only have 150 milliamps on this tube filament. It will operate probably very well anywhere between 100 milliamps and probably 200 milliamps. Now, don't put 200 milliamps on. Don't say, hey, will SRT Amplification said I put 200 milliamps on the filament lining. Didn't say that. Well, you can, but your tube may not last very long. So there's a set resistance designed into these things, and that's what really drives the train on all of this. So what they're saying in this thing is, at 50 volts, you should have 150 milliamps running through this filament because of how we design the windings inside. Okay. Now a lot of people will take their multimeter, their ohm meter, and they'll go between pins 3 and 4, which is the filament, heater filament, and they'll get a reading of, you know, 180 ohms or something like that, and they'll say, well, I thought it was supposed to be 333 ohms. Well, the thing about resistance is resistance is directly proportional to the temperature. So as the temperature of that filament increases, the resistance will also go up. So you really have to know what the resistance is this thing is designed to operate at once it's heated up. So basically the only thing we've got to go off of is this is what it should be. So we're going to use these raw numbers here, and keep in mind this 50 volts across here may not be exactly 50 volts, and the resistance of the winding may not be exactly 333, but we're just going to use the math in this for our design anyway. Now, you know, I've heard a lot of people say, well, if I put a 50 volt tube filament in there, I'm only going to drop 50 volts across it. Well, that's not true, because if I put 120 volts across this single filament, I'm going to drop 120 volts across it. I'm not going to drop just the 50. I'm going to drop the whole 120. So when you go back to this thing, it's about proportions. You have to get the proportions correctly in order for 12 volts. You have to get the proportions correctly on all of these elements in series with each other in order to get the 12 volts across this one, 12 volts across this one, 50 volts across this one. The remainder, you know, I think 11 volts across this one, and the 35 volts across this one. And that would give you the correct current that these things need. Now, will it be 150 amps? Maybe not, but whatever it is, it's going to be the same through all of them because this is in series. Okay, so that's what we're talking about now, is the series. Later, we're going to talk about a little bit about putting filament windings in parallel, and it comes with its own pitfalls and advantages and everything like that. But so let's work through this and see what we can do. So our first tube, we're going to say, is our 50, which we already said was, so let me write this down first. So this is something you have to absolutely know. So E, which is electromotive force, is voltage, equals I, which is current, R. Okay, so basically voltage equals current, voltage, your electromotive force in volts equals your current in amps times your resistance in ohms. Okay, so basically what we have here is we know that we have a 50 volt tube that we're wanting to run, and we want it to run at 150 milliamps or 1.50 amps, and we're wanting to know R. Okay, so it's really easy. All you do is divide both sides by current to get rid of your current on this side. So basically what R is the 50 divided by 50 volts divided by the 150 milliamps, and that gives you your 333.3 repeating 3. Okay, if somebody puts that in their calculator, that's probably what they'll get. Let's see, 50 divided by 0.15 equals, yes, exactly. Okay, so let's write that down over here on a separate sheet of paper. 333.3 ohms. So if you were to need to put a resistor in there to replace that tube in order to get your 150 milliamps to run through the circuit, you would replace it with a 333.3 ohm resistor, theoretically. Okay, so we got that. Now we have these two 12 volt devices, and again, this is not exactly 12 volts. When you see a 12 AV6 or 12 AT6 or whatever, Usually, you know, that's just what they call it. It's probably 12.6 volts, but we'll go with 12 volts just for argument's sake. Your tube will operate just fine at 12 volts. So let's put that in there in the formula, and so that would give us 12 equals 150 milliamps, or 150 or 1.50 amps times R, which gives us a resistance of 80 ohms for the two 12 volt tubes. So let's write that down twice. 80 ohms, 80 ohms. Okay, so that's what we got so far. Now we got the 35. The 35 is going to be the same, done the same, exact same way. We're going to have 35 equals 0.15 amps times R. R is going to equal 35 divided by 0.15, 233.3 repeating 3 ohms. Okay, so that's what we got. 233.3 repeating 3 ohms. Okay, so that's 4 of our elements that we had in here. The unknown at this point is, what is this drop-in resistor? What should this drop-in resistor right here be? So let's go ahead and put the 75 in there, since we already see this. Somebody's done the work for us, right? And then we'll go back and figure out how we can solve for that. Okay, so let's put the 75 in there. $75 ohms. We're going to add all of these up, and we're going to come up to a figure of 801.6 ohms. Okay, so if we reverse engineer this and put this back into our formula where we said that R equals E over I, okay, and now we know R, which is 801.6 ohms, equals, and we know our voltage, our line voltage is 120 volts across all of these elements, over I. Okay, so now how do we solve for I? So I would equal, remember our original formula, it's actually easier to go back to that. E equals I times R. So I equals E over R. Okay, so we just go back down here and we go 120 volts over 801.6 ohms. We stick that into our calculator. And that gets us 120. There it is. 120 divided by 801.6. That gets us I equaling 0.1497 amps. So really, all intents and purposes, I equals 150 milliamps, which is what I should equal because it's in series. So you see the math works out just fine, okay, with that 75 ohm resistor in there. Now you're designing this, you don't know the 75 ohm resistor. Let's say you've got a tube that's got 6 volts, or you've got 3 tubes that's got 12, or you got 2 35 volt tubes, or 25. You don't know. you don't know. You can't find a single example of this on the internet. What do? Well, I will show you. So if we go back to our formula here, where we added up all the ones that we did know, the resistances that we did know, we would have came out to, before we added the 75 in, we would have had 726.6 ohms. This is before we added in the 75 and got the 801, right? So again, we go back to our formula. R equals E over I, right? Okay? So we have 726.6 ohms plus X ohms, that dropping resistor that we're trying to find, right? Equals 120 over 0.15 amps, right? Keep my values there. Okay, so that's too easy, right? And we already said that this 120 divided by the 150 was 800, approximately 800 ohms, right? If you do the math on that. So when we do the math on this, we have 120 volts divided by 1.50 amps, and that comes up to 800 ohms on this side. So now we can solve for ohms because we got ohms on both sides. So what I'm going to do to solve for X ohms is I'm going to take the 726.6 ohms and subtract it from both sides. I've subtracted from this one because this is addition right here. I give it X ohms, and then on this side I'll get 800 ohms minus 726.6 ohms, and that basically gives me approximately X equaling what, 73.4 ohms, which is very close to what we had, which, you know, approximately 75 ohms. So that's how they came up with that 75 ohm resistor. The math works. Even if you didn't know that 75 ohm resistor, you could work through this with everything you do know and find out what that resistor needs to be. So that's how that works. That's just using Ohm's law. Now, let's talk a little bit about paralleling. So in most modern day amps, you'll have a transformer winding, you know, your primary, your secondary. And this right here will be, you know, what's rectified. And then down here, usually, you know, you'll have at least one filament voltage rail. Let's say this one is a 6.3 or 6.3 volt rail. Okay, so this is our 6.3 volt supply for our filaments. Let me draw this out on another sheet of paper here, a little bit larger. So if we zoom in on this one portion of the primary or the secondary side of a transformer, our 6.3 volt side, we will have all of our filaments, okay, coming through and connecting to this rail. Each one of them gets the same amount of voltage, okay, regardless of what their resistance value is on the actual filament. So this is great because I can mix and match different types of tubes. I can put a tube in here like a 6L6 that draws a 1.5 amps on its filament, and I can put a 12AX7 in here that draws, you know, 150 milliamps. It doesn't matter. The pitfall in this is this. and I'll get to how you can put a 12AX7 in here in just a moment. But the pitfall to this is all of these currents add. According to Kirchhoff's law, when you come to the way my professor used to put it is all your gazenas must equal your gazatas. So if I've got, you know, X amount of current coming through here, and X amount of current coming through here, and X amount of current coming through here, and X amount of current coming through here, all of those gazenas, everything going in, has got to come out. So your currents add to each other when you have loads in parallel like this. Basically, that's as simple as I can put it. Whereas your current in the series filament that we just looked at stayed the same, and your voltages added, your voltage drops added. Okay. This is exactly opposite. In parallel, your currents are adding. Why is that important? Well, it's important because if I go to a system that was designed one way and I want to modify it, it could change things. These windings may not be able to hold current of that magnitude. For instance, let's go to the 12AX7. We pull up the 12AX7 data sheet here, and you can see that a 12AX7 has on pins 4 and 5 the filament winding all the way across in series, but there's a center tap on this filament winding. Let me zoom in here. If you look at pin 9 center taps that winding, that filament, heater filament. Okay, now if we look over here, we see that if we put the two parts of the filament in series with each other and put 12.6 volts across it, we should have a current of 150 milliamps or 0.15 amps. But if we lower the voltage and want to run this thing on a 6.3 volts system, we put them in parallel and we get 300 milliamps. Now you might ask yourself, how in the world can we lower the voltage across the same filaments and now get well, I will show you how that works. So let's just take a single filament here, 12AX7, okay, and I put 12.6 volts across it, and that comes up to approximately, I think, 84 ohms. If I use the 12, comes up to 80 ohms if I use just 12 volts, but if I use the 12.6, it comes up to 84 ohms. And when you do the math, this works out to 0.50, or excuse me, 0.150 amps, or 150 milliamps. It just does. It works out perfectly in the math. Now, if I take this same filament and I split it in half, okay, what have I done to the resistance? That resistance is now in half. Okay, so now what I have is I have a filament winding in parallel with another filament winding, and one of them is 42 ohms, half of the 84, and the other one is 42 ohms, half of the 84, right? And then I put these in parallel. Now the parallel resistance to this is 21 ohms. Okay? So 21 ohms at 6.3 volts is 0.3 amps, or 300 milliamps. Okay? And you can do this either way. You can either say that, you know, 42 in parallel with 42 is 21, or you can say that 6.3 volts across a 42 ohm resistor gives you 150 milliamps, and 6.3 volts across another 42 ohm resistance gives you another 0.15 or 150 milliamps, and those two values, because they're in parallel, have to add up to give you a current of 150 milliamps running through this, 150 milliamps running through this node, for a total of 300 milliamps. So when you go back to this right here, and this, let's say in this instance I have you know, this is actually a, let's say a 6L6, okay, and this is another 6L6, but this is one 12AX7 with two 6-volt filaments in parallel, okay. If I would have had a whole nother rail over here of 12-volt source, okay, I would have only had 150 milliamps running through it. This, in this instance, I have 300 milliamps running through it. Okay, so when you go to design amplifiers, you have to realize that my current adds on this, and that, you know, you can't be so close in this that you can't, you know, go up of 300 milliamps or whatever. And then also keep in mind that everything that you have on this side, if you're going to fuse it on this side, it's going to be, you know, in this case, it's going to be lower. So that's going to adjust what your power supply and everything is going to be fused on that side. So everything's going to be dictated by this. So I hope this helps both in the design process and your way of thinking about things. Basically, the way I think of tube filaments is I just think of them as resistors, and those resistances is really what I'm trying to match up, not so much the voltage. Yeah, you can think of it as, I got 50 volt tube, it's going to drop 50 volts across it. But when you're talking about in series, you have, the only way it's going to drop that 50 volts across it is if all of your other drops in that line is proportional to give you that 50 volts. Don't just think I can put 120 volts across a 50 volt filament tube and I'm only going to drop 50 volts across it. I'm going to drop the whole 120 volts across it. So I think that's the key to this. Is once you understand that, then you're good to go. But I hope you've enjoyed this video, and please like and share. If you like and share it, hey, like and share it even if you don't like and share it. But also subscribe and hit that little bell there, and you'll get notifications. And until next time, keep the tubes alive.